Welcome to the Master the NEC podcast, the ultimate destination for anyone passionate about the electrical trade. Whether you're a seasoned electrician, an eager apprentice, or just someone who wants to dive deep into the world of electrical work, you've come to the right place. Join your host, Paul Abernathy, a true authority in the industry with over 38 years of trade experience, as he electrifies your mind with in-depth discussions, expert tips, and valuable insights that will keep you ahead of the curve. Each episode, Paul will illuminate the complexities of the trade, decode the National Electrical Code, and share the latest industry trends, all while empowering you to take your electrical career to the next level. So, gear up, plug in, and get ready to supercharge your knowledge, because with the Master the NEC podcast, the power is in your hands. Now get ready, here is your host, Paul Abernathy.
Oh, what up, everybody? Welcome to another episode of Master the NEC, the podcast where I talk to you about anything electrical, code, theory, application, hiring, firing, marketing, promotion, whatever it is about the electrical industry. I'm here to help you and answer questions for you. Of course, you can always submit me questions over on our website, fasttracksystem.com. You go over there and you'll see in the navigation, there's a Let's Ask Paul link. Click that link and you can submit a question to me. I'm more than happy to answer those in podcasts. And in many cases, I will respond directly to you personally in an email answering your question. But it's been a great resource now for many years. And I want to thank everybody out there for participating in it. It really helps us get answer questions and dispel some myths out there or misconceptions that are obviously running rampant on all types of social media platforms today. And so we like to make an effort to kind of clear those things up when we get an opportunity. Today's episode is going to be a very impactful one. So I want you to really understand that this one could be about an hour long. So it's going to be long. I want to tell you that up front because we are going to unpack a lot of things today. Talk about misconceptions. We're going to talk about GFCI function. We're going to talk about the misconceptions. We're going to talk about generators, bonded versus unbonded or floating generators, and the application, the hazards that it can be involved with both, how you would use each one of them properly. I'm going to explain certain concepts that are going to be very elementary in how I explain them. So again, I'm hoping that you listen to our podcast, but I'm hoping that this one in particularly, you do listen to in its entirety, because again, there's so many things that we're going to unpack in this one. And I've been waiting to do this one because it's one of those things where I do videos on generators and GFCIs and understanding their function. And so many comments come in about the GFCI will work regardless of this or that or this or that. And you're wrong, Paul. And I'm like, okay, well, today we're going to explain all of that so that when you walk away from listening to this podcast, and y'all all know I love podcasts versus doing videos, because I believe that people should sit down with headphones on and just listen to a podcast, or take your shower and have one of your devices in there that plays a Bluetooth. And I really think that people probably don't listen to podcasts because in a podcast, I have to paint you a mental picture. And painting you a mental picture forces me to be as detailed in my verbiage as possible. And I think that's what ends up making better electricians, because you're able to listen, extract it, and apply it. And that's why I just love podcasts. And I love if I didn't do another video ever, that I wouldn't care. I just love podcasts, right? And because I think that it's a medium that is old school. Radio's radio, old school. I've been doing this well over probably close to 2 decades now when it comes to podcasting. And it's just a medium that makes you have to concentrate. And so I like doing it. So today we're going to talk about the truths about GFCIs. We're going to talk about UL 943. We're going to talk about floating or unbonded generators. We're going to talk about current path, current flow, how they operate. We're going to get rid of some myths and try to give you some real fundamental knowledge that you can hopefully share this with other people accurately rather than spreading misconception. Now, there are few electrical devices that electricians use every single day that are misunderstood more than ground fault circuit interrupters. Very few. There's a lot of people that just think they understand ground fault circuit interrupters, GFCIs, and how they function, and they really just take it for granted. In fact, I could probably ask 10 electricians how a GFCI works, and you're probably going to get 10 different answers. You might have one say, well, Paul, it senses current from the ground. Then you have another one that says, well, a GFCI doesn't even need a ground to work. Then you'll have another one that might say, well, then how in the world can it be a ground fault circuit interrupter if there is no ground, when the code allows you to use it when there is no equipment ground present in certain applications of existing installations? They might say that. And so that's where the wheels start coming off of a conversation, because all three of these people's answers are focusing on the term ground, when we really need to talk about is current. And so I think the misconception is when you see ground fault circuit interrupter, that they forget this whole conversation needs to forget about the term ground. That's just the name of the device. We need to understand how the current, where did the current leave? Where did the current come back? And did all of it return through the conductors that the GFCI is actually monitoring? That's the entire foundation of today's podcast. We're going to take it one step further. We're going to actually put that GFCI on a portable generator. We're going to use it and explain it when there's a floating unbonded generator winding, which, you might get a generator that is, unbonded generator. It might have been previously connected to a dwelling, and now you're taking it and using it as a work generator out on a project, and it's been altered in some way. Or you may have a bonded generator that ultimately, in a storm, you end up connecting it to your dwelling or something like that. So we have to unwrap all of that stuff. So not only are we going to explain the applications for generators and things like interlocks and transfer switches, because I think that's an important topic today, but we're also going to understand the relationship of the GFCI device, how it interacts in these systems, okay? So that's what we're going to kind of unpack today, okay? So we're going to connect that generator to a dwelling through a panel interlocked, and it doesn't switch in neutral. And then when we're finished, you're going to understand why no return path can create a problem, but too many return paths can also create a problem. And sitting right there in the middle of all of that is this simple GFCI device that's asking, did the current that went out come back through me? And if it didn't, how in the world can I function properly if it all came back through me and I didn't notice an imbalance? All of that's going to be talked about in today's episode and clear all of that stuff up for folks. Okay, so when we start into this, I just want to, for a second, let's focus on something. I want you to temporarily, okay? And when I say temporarily, I want you to temporarily forget the name ground fault circuit interrupter. I know that sounds strange, but the word ground causes people to create this mental picture that isn't entirely accurate. They picture a GFCI as somehow monitoring the green or bare equipment ground and conductor. That's what they picture. That's what you see when you see the word ground. So I want you to forget the word ground, okay, as we do this discussion, right? Almost like they think of the way that it monitors it. It thinks it's dedicated to that equipment ground. It thinks it's almost like there's this electronic policeman sitting inside this receptacle watching the ground wire saying, hey, I just saw electricity on that ground wire. I need you to trip. That's not fundamentally how a Class A GFCI operates. Okay, so we want to make sure we're clear with that. So we're gonna definitely hit some fundamentals for you. Under UL 943, that is the standard for ground fault circuit interrupters, if you're not aware of that. UL identifies a Class A, which is typically what you're going to be using, for example, in a normal personal protection for kitchens and bathrooms, whatever, in your dwelling. Those are Class A GFCIs. And under UL 943, they're called personnel protection devices. And this is the receptacle type GFCIs, portable GFCIs used on construction sites, circuit breaker type GFCIs, UL currently describes UL 943 Class A devices as intended for grounded neutral systems. That's the intended system that these things are supposed to be used on. Fundamentally important. And when we're talking about typical Class A circuit breakers, GFCI, UL identifies that Class A markings with a 6 milliampere maximum ground fault trip threshold. Now, you've heard us all say nominal 5 milliamps because the way it is, if it's 4 or less, it's not going to detect it. And if it's 6 or more, it's going to detect it. So we usually use 5 milliamps as the nominal because 6, right, is the max. 4 is the min. So we always just say 5 milliamps. That's the nominal. Okay. Now, but what is it actually sensing? That's what's, I guess, the most important thing. What is this GFCI really doing? And that's what's going to matter. So in order to do that, we need to crack it open. And when we crack it open and we start digging into this, you'll hear a lot of people talk about this little GFCI sensing transformer is the donut. Okay, it's inside the GFCI. It's a sensing transformer. Electricians will commonly describe it as, again, a little donut or a toroidal current transformer, or you might hear somebody say it's a toroidal coil. Okay, so on a typical 120 volt branch circuit, or just say 120 volt circuit in general, the ungrounded conductor and the grounded conductor, both of them actually pass through that sensing transformer, that donut. So let's keep this ridiculously simple, okay? If I've got 5 amps leaving through the ungrounded conductors, going through that toroidal coil or that donut, and I've got 5 amperes returning through the grounded conductor through that toroidal coil, that sensing transformer, and obviously alternating current, it's traveling in opposite directions, so the current's moving in opposite directions through that toroidal sensing coil. Each conductor creates this magnetic effect, right? And expanding and collapsing magnetic field. You probably learned that back when you were going through trade school, right? Rapidly expanding contraction as the current changes directions and alternating current. Well, in this case, when you run the two conductors through it, then the magnetic effect is essentially canceled out. So the coil's not going to be picking and sensing anything in the circuitry. So from the perspective of the sensing circuit, current out equals current back. Everything is good. It's not picking up any magnetic field. It's just canceling itself out. Okay. So the GFCI doesn't care that 5 amps is flowing. That's important. 5 amps doesn't bother it. Shoot, 10 amps doesn't inherently bother the GFCI sensing function. What the GFCI actually cares about is the difference between the currents passing through its sensing transformer, that donut. Okay. That's what it's sensing. So now let's create this fault condition. So I've got 5 amps that is going out through the breaker, through that toroidal coil, leaving on an ungrounded conductor. Okay. But somewhere in the path, I've only got 4.995 amperes coming back through the grounded conductor. I'm missing 5 milliamperes. Well, you have to ask yourself, now, where did that 5 milliamperes go? Here's the important part. The GFCI doesn't have to know where it went. It just knows it didn't come back through the monitored conductors. Maybe it traveled through an equipment grounding conductor. Okay? Maybe it went through a bonded metal. Maybe it went through piping. Hell, maybe it went through concrete. Maybe even through the earth. Sadly, maybe even through a person's body. But whatever path it took to get back to the source, that current bypassed the normal monitored return path. It did not fully come back on the neutral. And now that magnetic field doesn't completely cancel out because now there's a differential current. So it does create an imbalance that creates the magnetic field. And that's what gets the GFCI's attention. Even OSHA describes GFCI operations similarly. They say in OSHA, it says the device compares current leaving on the ungrounded conductors with current returning through the neutral and responds when an imbalance occurs. OSHA also makes it clear that a GFCI monitors current leakage. It is not a device for verifying continuity of an equipment grounded conductor. That is not what its function is. It is looking for imbalance on the intended circuit path. So here's our first big takeaway before we dig even so deeper into this that you start going, okay, this is getting deep. A GFCI is functionally a differential current device. It is not a green wire or bare wire or equipment grounding conductor detector. That is not what it functions. So let's get rid of that right up front. Next, let's talk about GFCI versus circuit breakers. Now, let's clear up another misconception. A GFCI isn't simply a tiny circuit breaker. Y'all all know this. A normal 15 or 20 amp branch circuit overcurrent protected device is concerned primarily with things such as overload, short circuit, things like that, okay? That's it. That's its main function. Overload, short circuit, ground fault. A GFCI has a completely different mission. So let's kind of picture ourselves here. Imagine I've got an appliance that's on this circuit. It draws 8 amperes. That's normal. It's fine. 8 amps goes out to the load. Load's drawing 8 amps. 8 amps comes back through the same circuit, through the neutral, through the toroidal coil. Boom. No magnetic field is generated. Cancels each other out. GFCI doesn't care. It's like, I don't care. Everything's good on my end. Take that same circuit. Somewhere in that circuit path, let's say we have insulation deterioration somewhere. And let's say we have 5 milliamps leakage onto something else, some other component. It has another return path. Okay, well, my normal breaker still sees 8 amps. That's all it's seeing. As long as it goes out and comes back, as far as the breaker's concerned, dude, I'm continuing to run. I'm good. Breaker says, I'm fine. Let's go. It doesn't care. That's nowhere near the overcurrent operating region for that overcurrent device. So it does not care. But the GFCI sees 8 amps out, but only 7.995 amperes back. Now we have a difference. That's why GFCI protection and overcurrent protection should never be taught as though they're doing the same job. They are not doing the same job and never have done the same job. Now, you may have a device that does all those things, like a typical GFCI circuit breaker. It's going to have integral overcurrent protection, but it's also going to have the GFCI protection built into it. And it still serves as a breaker, obviously. But don't interconnect the two. That's also why equipment ground fault protection, personnel GFCI protection, AFCI protection, and ordinary branch circuit overcurrent protection should not be thrown into that one bucket just because they can all cause a circuit breaker to actually open because they use different technologies, they're looking at different hazards, and they have varying operating criteria. They're all operating differently. So we don't lump them in the same basket. They all have their own purpose and their own role. Now, the next thing that we run into, it's logical, is say, but wait a minute, wait, Paul. There's no equipment ground. Okay, so now we get to one of the biggest myths we have out there. Somebody finds an old 2-wire branch circuit, okay? We've got an ungrounded conductor and we've got a grounded conductor, just a black and a white 2-wire system. But we don't have an equipment grounded conductor. And somebody will say, you can't use a GFCI because a GFCI needs a ground to operate. Well, hopefully by now you understand that that is not the case. It doesn't need a ground to operate. The GFCI doesn't require an equipment grounded conductor through its sensing transformer. It doesn't run through its toroidal coil. What it needs is a difference between the monitored conductors, the hot and the neutral. That's what it's looking for. So the GFCI is not taking the place of a ground connection or the establishment of the ground, the low impedance affected ground fault current path. That's not what it's replacing. let's remember what the GFCI is doing. It's only looking for the differences between the monitored conductors when it comes to current flow. That's it. So now, let's say a person contacts the energized conductive part. Now, current leaves the ungrounded conductor through the person, and let's say it finds some other conductive path back to the grounded system and ultimately back to the source. This is why in a system like a bathroom, if it's an existing and it's a two-wire system, you replace it with a GFCI. The concept is there is no equipment ground present, but we want to afford some type of safety because it could be where you become in contact with some other alternative path like metal piping system or what something else that ultimately is maybe bonded back to the source. Now, maybe this path is the earth. Maybe it's a grounded pipe. Maybe it's structural metal. Maybe it's some other bonded conductive object in close proximity. The specific path isn't really the point. The point is that the current that left through the monitored ungrounded hot conductor, it actually doesn't return on the monitored grounded conductor. It may get back some other way, but it's not coming back on the intended path. Now, the GFCI sees this imbalance. That's why GFCI protection can still provide important personnel protection on an otherwise ungrounded branch circuit. But let me be very clear. Installing a GFCI does not magically create an equipment grounded conductor. Another falsehood that I see a lot of times on various home inspector channels and forums and platforms and electricians that say, just throw a GFCI in there, that'll replace the need for an equipment ground. That is not what it does, okay? If the receptacle has no EGC, equipment grounded conductor, then guess what? It still has no EGC. All you're adding is differential current protection. That is why you're adding the GFCI. And it's better than nothing, especially if something happens and the system deteriorates and it finds another path back and that path is through you. You definitely want to make sure that that GFCI is going to function. But as we saw earlier, if there's no return path, then there's no current flow. So it can't solve everything, but it does create a situation where if you did have that alternate path back to the source and you become in contact with that, it will protect you or make an effort to protect you, right? So you're not magically grounding the enclosure, grounding the appliance, or installing a low impedance equipment grounding conductor back to the source. You're not doing that when you put that GFCI into a two-wire ungrounded system. Or branch circuit that's ungrounded, okay? Just because you put that GFCI in there, you're not creating a magical grounded system at that location. That's not. Those are totally different concepts. Now, I guess that leads us into understanding the return path is everything and understanding current flow. So this is where I want to actually slow down a little bit because this concept takes us directly into generators, and we're going to start. We understood the basics, the concepts, and we spent 23 minutes explaining this, so you truly should understand how a GFCI functions and how the current path has to flow and what the GFCI is looking for, what it can do, and what it can't do. But then we had to slow down a little bit because we have to think of this return path now. Electricity needs a circuit to flow. I know this sounds elementary, but again, that's why you have a switch. You flip the switch, you break the circuit path, you flip the switch back on, you close the path, and the circuit and the current flows. Very simple concept, right? But electricians sometimes become so focused on the grounding rules that we actually stop drawing the actual circuit in our head to understand that it has to be a complete system in order to function for current to flow. Remember, current does not simply disappear into the earth. It doesn't dissipate out. Current does not leave a generator, go to the earth, and then all of a sudden just vanish. For sustained current to flow, we have to have that path back to the source, a closed loop. So if circuit's current leaves the source through a person and travels into the earth, I want you to ask me something. Paul, how does it get from the earth back to the source winding? That's an incredibly important question. And that brings us to floating generators or unbonded generators. So you have to always ask yourself, Paul, it could flow through me and it could go through me to the earth, but doesn't it have to get back to the source? How does that happen? And so let's talk a little bit about a floating generator and unbonded generator. If it's a truly floating generator or an unbonded generator, so let's take this example. I have a portable generator completely by itself. You used it for, maybe job sites, totally isolated. It's not hooking it up to a dwelling. It's just a generator you pull out to work on a job site. It isn't connected to a dwelling. It's just sitting there. You take it out, you use it for a project. For purposes of this example, the winding is truly isolated. So it is a floating neutral. There is no connection between the neutral. There is no connection to the frame. It's just a truly isolated generator. Neither circuit conductor has any intentional connection to the generator frame or the earth. Okay, none of that. No. So electrically, what we've got here is a floating source, an unbonded floating source generator. Now, UL makes an important point here. UL 943, Class A GFCIs are intended, okay, do you hear me? Intended for use in grounded neutral systems. That's worth remembering while we're discussing this hypothetical isolated source. Now, let's take one conductor from that generator winding and run it through a GFCI. Okay, so we're creating this system in our head. I'm going to go from the generator winding out, and I'm going to be supplying this GFCI receptacle. Now, let's imagine somebody contacts that conductor while standing on the earth. Okay, so it's coming from the floating generator, from the winding, through the GFCI, and it's maybe it's in a cord, and I'm coming in contact with it, and I'm standing on the earth barefoot. Let's just say that. Let's follow this circuit, how it would flow. From the generator winding, through the conductor, through the person, onto the earth, and then remember that important question we have to ask, and then what? That's an important question, isn't it? And then what happens? Where is the connection from earth back to the other side of the generator winding to complete the circuit? If the winding is truly isolated, there isn't an intentional one. So what we have is generator to person to earth and one big ass question mark. We haven't completed the circuit back to the source. That means that the first conductor to earth contact may result in very little current because we haven't intentionally provided a conductive return path to the source. It's not there. And now think about that GFCI. If little or no current flows outside of the monitored conductors, what differential current is the GFCI supposed to be detecting? Because there's potentially none. That doesn't necessarily mean the GFCI failed. That doesn't mean that it's no good. There may simply be insufficient differential current to actually make it operate. OSHA has historically recognized that electrical characteristics in certain isolated portable generator configurations, its construction rules and interpretations distinguish generator circuits whose conductors are insulated from the frame and grounded surfaces from grounded generator systems. Distinct difference in the different types from an isolated portable generator versus one that is actually bonded to the frame. Now, nobody is going to hear that and say, quote, actually, I think somebody's going to hear that statement. They're going to actually hear that statement and say, wait a minute, Paul, I'm interpreting from that statement now is that a floating generator can't shock you. Absolutely not what we're saying. So don't make that leap. That's what I hear this all the time. They say, well, Paul, if it's not, if it's not bonded, then there's no way for current to get back. There's no way that you can get shocked. That is not true. Now, let's do not make that leap. Real systems aren't perfect classroom drawings. In reality, we've got capacitance, we've got insulation leakage, we've got connection loads, we've got electronic filtering, damage that could take place between point A and point B. We have multiple pieces of equipment that could be involved, things that are plugged into the generator, moisture, water, rain, other contaminants, and possibly another fault somewhere else in this system. Any of those things could establish a reference or create another current path. And once that happens, everything changes. So it gives you the false impression that the floating generator is safer. So the lesson isn't a floating generator is shockproof. The lesson really is the first conductor to ground contact on a truly isolated source may not establish the same fault current path that exists on a grounded system. Dude, that's not myth. That's electrical theory. That's truth. And understanding that theory makes the rest of this discussion going to be much easier for you to understand complete systems, complete loops, and how it gets from point A to point B. Now, since we established that that first one may not cause the device to operate, we need to think about, what about a second fault? So now let's leave that first fault in place. It's there, it's sitting there. It could create live parts. It could be energizing something that's waiting like a ticking time bomb. Now, somewhere in the floating generator system, let's say one conductor becomes unintentionally connected to the frame or some grounded conductive component. Maybe somebody didn't even know it happened. Maybe somebody contacts an opposite conductor. Okay. One side of the generator winding through the person, through the grounded conductive system, through our first fault, and then back to the opposite side of the generator winding by the second fault. Well, guess what? Now we have a complete circuit. Now significant current can flow on that generator that you thought was unbonded, floating, and due to a series of events can create this secondary condition. Now that current can flow. And if some of that current bypasses one of the conductors monitored by the GFCI, now we've created that differential current the GFCI was designed to detect. So again, follow the current. Don't simply memorize it. Floating generators good, floating bonded generators bad. This is not electrical education. That is not education by saying that. Don't simply say floating generators are good, bonded generators are bad. It's much more detailed than that. That is not good electrical education to say that. You have to understand the circuit and understand when you would use one over the other. And we're going to get into that because now I'm going to go from that generator that's sitting out in a field that needs to be bonded so that if it comes back on the earth, it can come through the frame. And that is truly a separately derived system. It's sitting there. It's not connected to a dwelling or any other system. Okay. That is a situation where we could actually have the GFCI function, giving it that proper path. Okay. Back to from the ungrounded conductor out back through the winding to the opposite. So that's what we're establishing. Okay. Not going to work for a floating generator for use out in the job site. Now, let's change it a little bit. Let's connect this generator to the house. This is where things get really interesting. Take the same portable generator that we've been talking about. Now, we're going to connect it to a dwelling using a proper generator inlet, and we're going to put a panel board interlock arrangement in it. We're going to not switch the neutral. So the interlock mechanically prevents the utility main breakers and the generator backfed breaker from being on at the same time. We get that. That's the whole purpose of the interlock. So we're preventing the generator from energizing the utility supply conductors while the normal source is connected. We don't want the generator to be connected to it. Good. That's all done. But here's the part that gets overlooked. A conventional circuit breaker interlock does not actually switch the neutral. We're transferring the two ungrounded conductors, line 1, line 2, but the grounded conductor, the neutral, remains connected. So when the generator plugs into the dwelling, the generator neutral connects directly to the dwelling's neutral system. And somewhere upstream at the service equipment, that grounded conductor is already bonded through a main bonding jumper to the equipment grounding system. Now think back to our floating generator scenario. When it was sitting out in the yard by itself, its neutral could truly be floating. But once I connect that same generator, connects its neutral to the dwelling neutral through an unswitched neutral arrangement, that generator winding is now has a connection to the dwelling's grounded conductor system and ultimately to the service bonding point. So in this case, the situation or the electrical situation has totally changed. This is a major concept. So people will say, my generator has a floating neutral. Okay, floating when? Floating while standing alone, or floating while you connect it to the premise wiring system where it intentionally connects to the neutral, and that neutral remains solidly connected to the service's bonding point. Those aren't necessarily the same electrical condition. It's vastly important that you understand the hazards involved with this. And of course, I'm going to break this down, but you can't just take one generator that's used in one application and then magically use it in another application and say, dude, it's just a generator, it's fine. So OSHA and the NEC will define separately derived systems as it is very distinctly, and it's clear. A generator system is not separately derived when its grounded conductor remains solidly interconnected to the service-supplied grounded conductor. You're not switching the neutral. If you're not switching the neutral, then it is not a separately derived system. It's just another system, just like an oven, just like a range, okay? So that brings up the next giant misconceptions. Why don't I just bond the generator's neutral? So we started out with this floating generator, right? And we used it out in the field, which was a wrong application because it needs to have a bonding jumper in it. And then we moved it over to the dwelling and we used the same floating generator. Okay, well, we're going to see where that would be right and why that would be right versus using a bonded one. So the question now, people say, well, vast majority of the generators that I buy out to use in the field, not on the house, but to use out on a job site, that they typically are going to be a bonded generator. I know I've got mine. I got a Westinghouse 9500. It had the bonding jumper in it. It's a portable generator. I use it for my house. I have an interlock system. So I had to move the bonding jumper out of it. And this is fundamentally, so people ask yourself, well, why don't I just bond the generator neutral? So somebody says, Paul, you spent the past 38 minutes explaining how a floating source may not have a ground fault return path. Why don't I just bond the neutral to the generator's frame? Well, because you're connecting that generator to a dwelling with an unswitched neutral. The neutral is already connected back at the dwelling's system bonding point. So you don't just take a floating generator that was improperly being used out in the field and all of a sudden put a bonding jumper on it and use it on a dwelling. And people do this when it's the exact opposite. You want to be a floating or unbonded generator if you're going to hook it to your dwelling and you're not switching the neutral. And then if it's a portable generator out in the field, then you want to have it be a bonded generator. So people ask this, well, why don't I just take my my generator, if it was a floating generator, why don't I just bond it? Shit, I'll just run a connection from the neutral to the frame. I'll just bond it. Well, because when you're connecting that generator to a dwelling with an unswitched neutral, the neutral is already connected back there. So if I add another neutral to frame connection at the generator, here's what I'm doing. I'm creating something that is potentially hazardous. I'm creating two neutral to ground connections, and the code is very clear about not creating case to neutral connections downstream of the panel, of the main panel. So if I have two neutral to ground connections, one at the dwelling service equipment, and then I have another one at the generator because I used a bonded generator on a dwelling, or I took an unbonded or floating generator and I put this jumper in there, and now I created a bonded because some electrician told me to. Now I've got a problem. Because now if you follow the circuitry, you follow the path, here's what you've got. You've got this generator neutral is connected to the dwelling's neutral, okay? So the generator frame is connected through the equipment grounding conductor back to the dwelling equipment grounding system, right? Because we're running the generator. It's a 4-wire system. We're going to run a neutral. We're going to run an equipment ground, and we're going to run two ungrounded conductors, right? So if you do this bonded generator out at a dwelling, and you've got this connection now, you've got the equipment grounded conductor, which goes back, and you've got the neutral that's connected together. They're both going back to the same location. Okay, you with me? So now, the generator frame is connected through the equipment grounding conductor back to the dwelling's equipment grounding system, and at the service equipment, the equipment grounding system and grounded conductor are bonded together with the main bonding jumper. Then at the generator, I've bonded them together again because I wanted to create a bonded generator, which you know by now you should not do if you're connecting it to a dwelling, but somebody does it, or they don't think about it. Now, the neutral conductor and equipment grounding path can form what's called parallel conductive path between those two bonding locations. And that is the problem. So you say, okay, well, Paul, I need you to illustrate how this creates a problem. Okay, let's break this down so it's so simple to understand where the hazards can happen. Normal load current now has another way home. Let's simply put a 120 volt load in the dwelling, and it's being powered by this generator. And you use a bonded generator on a system where it does not switch to neutral. So you've got parallel paths. So current leaves one side of the generator windings on the ungrounded conductor. It goes through the load, whatever that load may be, because you're running generator. Now it returns on the branch circuit neutral. Everything is fine so far. When that current reaches the dwelling neutral system, where should it go? Back to the generator winding through the neutral conductor? Well, that's our intended normal current path if you're powering this circuit through the generator into the dwelling. But I just gave it another path because I'm using a bonded generator that's creating parallel paths. Because the neutral is bonded to the equipment grounding conductor at the service, and I bonded the neutral to the generator's frame again, to the equipment ground, I now potentially have neutral current flowing from the service bonding point through the equipment grounding system to the generator's equipment grounding conductor, through the generator's frame, generator's neutral bond, and then to the generator's winding. That's a second conductive path, not the intended neutral path. And again, remember, current's going to take all paths available proportional to the amount of impedance of that path. It's going to travel on all those parts. Now, some normal load current can divide between the grounded conductor and the equipment grounding bonding path according to impedance, as we just said, on those parallel paths. And that's exactly what we don't want to happen. Equipment grounding conductor isn't supposed to become a second normal neutral conductor. And you just created that. You just paralleled the neutral. Its job is not to routinely carry normal load current. Its job is to provide an effective path for fault current when something goes wrong. That's a completely different function than what you inadvertently did by using a bonded generator on a system with an interlock that you did not switch the neutral. Now, OSHA's generator rules specifically distinguish generator frame bonding from the neutral bonding required when the generator forms part of a separately derived system. So this is why the statement that people make is a bonded generator is safer. That's actually incomplete. And some people say a floating generator is safer. That is also incomplete. The real question that we should be asking about the use of a generator is, how is this particular generator connected to the particular system? Am I using it as a standalone at a job site in a field? Or am I going to connect it to the dwelling's premise wiring system? That's fundamentally what we have to decision, not whether one is safer over the other. Because used in the improper condition, they are equally dangerous. Now, that interlock didn't do anything wrong, okay? So let's make sure we're clear about something. I'm not saying that a pan or interlocks are inherently dangerous. That's not the lesson. That's not what we're talking about. The interlock is accomplishing its intended job, right? It's preventing simultaneous connection of the generator power to the utility power. It's doing exactly what it's designed to do, so one's not on when the other's on. The issue we're discussing is how we're treating that neutral. A mechanical breaker interlock normally operates the breaker for the ungrounded conductors. It does not turn the service neutral on or off. Doesn't have anything to do with that. Doesn't break it. Doesn't change the situation. So if the generator is connected through an arrangement where the neutral remains solid, and that's what it's going to be on most all of those interlock systems like that, you need a generator grounding and bonding configuration appropriate for that unswitched neutral system. You cannot simply say, quote, this generator came from a factory with a neutral to frame bond, so I'll just plug it into anything and say, you know what, it's just a generator, it'll work. Because that's not accurate. That manufacturer may not have intended for that generator to be used in the application that you're trying to use it for. Nor should somebody randomly start removing a factory bonded connection without understanding the generator's listing, the manufacturer's instructions, and transfer arrangement, understanding how you're actually using this generator. And that's a problem. When we have storms around the country, people sell generators. People just go grab generators. They start hooking them up to systems. Electricians get involved. They don't understand these concepts, and they don't understand the difference between a bonded and an unbonded generator. They get confused. And that's a problem. Each system has to be evaluated on their own to determine what we actually need. You got to look at the generator. You got to look at the inlet. You got to look at the cord. You got to determine how you're going to transfer it. You got to look at the neutral configuration. You have to understand the service bonding points, all of it. You got to understand all of this. Now, conversely, somebody's going to say, well, Paul, I like to use those little transfer switches that does switch to neutral. So how do you deal with that? So what changes when we actually switch to neutral? Okay, now let's change this equipment out. We're not going to do an interlock. We're going to put a transfer switch in. So instead of leaving the neutral connected, the transfer equipment actually switches the neutral the same as it switches the ungrounded conductors. Perfect. So when we're on utility power, we've got the normal utility connections. When we transfer to a generator, that line 1 and line 2 from the utility disconnects, and the utility neutral is disconnected from the generator supplied system. So it's isolated. Everything's switched. Now, the generator grounded conductor is no longer solidly interconnected with the utility supply grounded conductor because it is switched. We've changed the entire grounding and bonding analysis at this point. This is where the generator can truly be constituted as a separately derived system. It is not connected to the other system. It's being switched. OSHA definition makes this distinction directly. It says, and I'll quote, a separately derived system has no direct electrical connection, including a solidly connected grounded conductor, to conductors originating in another system. It's totally separated. OSHA also requires the neutral to be bonded to the generator frame where the generator is a component of a separately derived system. So that generator that's sitting out in the field that you're using, portable generator, you're using it as a separately derived system. So the neutral is to be bonded to the frame because the OSHA requires that. So here's a simple way to understand that. If we have an unswitched neutral, we have line 1, line 2, those are switches. The neutral's not switched. This is what you do every day on an interlock. The generator neutral remains interconnected with the dwelling's grounded conductor system. Do not establish a second neutral to ground bond at the generator. Thus, you need to use a floating or unbonded generator when you're connecting it directly to a dwelling. Make sense? Especially when you're not switching the neutral. If you're switching the neutral or you're using one of those transfer switches or you're doing whole house transfer or whatever you're doing, then you have line 1 switches, line 2 switches, and the neutral switches. Now, we've electrically separated, the grounded conductor from the normal supply. We're dealing with a different system configuration, and the separately derived system bonding requirements become applicable at that point. And that's why I never want an electrician to memorize something in their mind and simply quote, generators should have bonded neutrals or generators should always have floating neutrals. Both statements can be wrong depending upon the installation. It really depends on what you're doing with the neutral, whether you're switching it or not. It's more deeper than just making generalized statements, okay? So all of this it ultimately is kind of circling us back to GFCIs. Now watch how everything comes back together here. Now go back to our truly floating generator. We were concerned about having no effective return path for the first conductor to fault or conductor to ground contact, okay? Now, with an incorrectly duplicated neutral to ground bond on the unswitched neutral dwelling connection, we can create multiple return paths, okay? So if we thinking about the two concepts, on a floating generator, we were originally concerned because there is no return path for that first. So how can the GFCI operate? There's no return path. And then what we looked at is, we said, wait a minute. What if we have a generator and we have a case to neutral connection at the generator, but we're using it on a dwelling? Now we're creating multiple return paths. That's a violation. So we've taken it to the extremes. One of them, we had no path or not enough path. And the other extreme, we used the generator improperly, and now we got too many paths. And then what's in the middle of all this? The GFCI. Right? It's still doing the exact same things. It's always looking for the imbalance. That's all it's doing. It doesn't care whether whether the conductors are called neutral, ground, bond, grounding electroconductor, equipment grounding conductor, grounding. It doesn't care about any of that. Its sensor transformer is simply asking how much current passed through me in any one direction and how much came back through me in the other direction. If those circuits don't balance within its operating characteristic, guess what? The GFCI trips. This is why grounding and bonding is not just definitions we make apprentices memorize. They determine current paths. The current paths determine what protective device sees. Okay? Now, a couple other misconceptions and things that we want to talk about, or myths, is does a GFCI protect me if I touch hot and neutral conductors? That's another major myth. Somebody will say, if there's a GFCI, I can't get electrocuted. That is absolutely not something you should rely upon. Let's say a person simultaneously touches the ungrounded hot conductor and the grounded conductor at the same time. So current flows from the hot through the body, back on the neutral. Now, look at it from the GFCI's point of view. Suppose your body and it passes through you. So suppose 50 milliamps goes through the person's body. 50 milliamps leaves through the ungrounded conductor being monitored by the GFCI. And ultimately, since you're touching the other side, 50 milliampere returns through the grounded conductor being monitored by the GFCI. So what's the difference here? Just because you're coming in contact with it and you're touching it. What's the difference? 0. The GFCI sees balanced current. What went out came back. Yep, potentially dangerous current is traveling through the person's body, and the GFCI doesn't blink an eye, doesn't trip. This isn't just theoretical wording I'm making up. UL's guidance for Class A circuit breakers, GFCIs, specifically says that in the instructions include information indicating that the user is not protected when contact is made with more than one circuit conductor. It literally says that. That statement alone should destroy the misconception that a GFCI somehow recognizes that a human being is being shocked. It doesn't. Remember, it recognizes imbalance. That's it. It doesn't care about anything else. It doesn't get personal. It's all it's looking for is an imbalance. And if you're a part of the circuit and you're not creating an imbalance, then you're just part of the circuit. So this next one here is for all of my home inspectors and people out there that test circuits and people that put stuff on social media. They go, but my plug tester says that the GFCI doesn't work. Here's another myth people have. Let's say you have an old 2-wire brand circuit with no equipment grounded conductor. Somebody installs a GFCI protected device. Then somebody comes behind them with one of those inexpensive 3-light testers, receptacle testers, with the GFCI test button built into it. They plug it in, they press the little test button, and the GFCI doesn't trip. And immediately on their report, it goes, see, I told you GFCIs don't work without a ground. No, what you've just demonstrated is that you don't truly understand how your tester works in your hand. Many external GFCI tester manufacturers will tell you that it manufactures an imbalance by taking a small amount of current from the ungrounded conductor and shunting it to the equipment grounded conductor. That's why these devices are 3-prong devices. It has the ground prong. Now, the GFCI sees current leave on the hot without the same amount returning on the neutral, obviously, because it's shunting it to the equipment ground. It trips. OSHA specifically describes this testing method as common GFCI testers shunt a small amount of current from the hot to the grounding conductor to produce the imbalance. So, what happens if there is no equipment grounding conductor in the circuit? The tester may have the path it needs to manufacture the fault current, or does it? Well, if there's no equipment ground, it can't have that path. It can't shunt anything. Therefore, it can't function. So the external tester may fail to trip a perfectly functioning GFCI. In fact, OSHA tells its own compliance personnel not to rely solely on a negative result from the external GFCI tester because circumstances can exist where the external tester gives a negative indication even though a functioning GFCI is protecting the actual circuit. That's an incredibly important point to understand. Don't confuse, quote, my tester couldn't create a test condition with, quote, the GFCI can't detect an actual differential current. Those are not the same statement. They are not the same statement. Now, how does a GFCI, so the next question that people ask is, well, okay, but don't all these GFCI devices have their own internal test button? Yes, they do. And somebody might ask me and says, Paul, if there's no ground and you've explained how the external test devices work, how does the test button on a GFCI work that's built into the GFCI? Well, Because the integral test function isn't simply depending on your branch circuit equipment grounded conductor the same way that a common external plug-in tester does, it doesn't do it the same way. The device's internal test circuitry deliberately creates a condition that the GFCI sensing system recognizes a ground fault type imbalance. Now, UL's application guidance for circuit breaker GFCIs says depressing the test switch causes a current simulating a ground fault to flow, so the internal mechanism should trip. UL also requires instructions on use of that supervisory circuit to indicate that these devices should be tested at least monthly. And of course, I know you all do. That's why understanding your test method matters. You should always know what exactly is my tester doing electrically, because a blinking light and a button don't replace electrical theory. Right? Now, a GFCI does not replace an EGC. Again, I will say this, and I hear this on social media all the time. We have to destroy another misconception before somebody takes this podcast completely out of context. And I know you will, because people do. If I say a GFCI doesn't require an equipment grounding conductor to perform differential current sensing, somebody online, somebody on social media is going to take that and shorten it and say, hey, Paul said equipment grounding conductors don't matter if you have a GFCI. That is not what I said. That's not even close. Nothing takes the place of an effective low impedance ground fault current path, the EGC. What we're saying is that the GFCI doesn't require an equipment grounding conductor itself to perform its differential current sensing function. That's all we're saying. The equipment grounding and bonding system provide functions a GFCI does not provide. The EGC, or equipment grounding conductor, establishes an intentional low impedance conductive path for fault current. That path helps produce enough fault current for the appropriate overcurrent device to open fast, very quickly. A GFCI is looking for a very small differential current associated with current escaping its intended current path. That's all it's doing. Yes, they work together. An equipment grounding conductor is vitally important to the installation, and new installations require it. But a GFCI also has its role and its functions and what it's trying to do as well. And they work perfectly together. One doesn't magically replace everything that the other does, folks. Remember that. A GFCI protected receptacle installed where no equipment ground conductor exists still doesn't suddenly have an equipment grounding conductor. It doesn't magically create an equipment grounding conductor. Is it safer without having anything? Absolutely. Does the code allow existing two-wire ungrounded branch circuits to be able to add a GFCI in it? Yes. But it doesn't magically create an equipment ground for faults. Understand the concept. GFCI protection does not mean grounded. Remember that. Grounding and bonding are not the same word, by the way. Generators also expose another problem in our industry. People use grounding and bonding interchangeably. They are not interchangeable concepts. When we connect conductive parts together to establish electrically continuity and it creates an effective fault current path, we're talking about bonding. When we intentionally establish a system's relationship to ground or to earth, we're talking about grounding. When somebody says, hey, Paul, my generator is grounded because the neutral is connected to the frame. When they say that to me, I immediately want to know exactly what they mean. I always follow with the question. I go, well, are we talking about the neutral to frame system bond? Are we talking about the generator frame to the EGC terminal being bonded? Are we talking about grounding electrodes? Are we talking about the dwelling grounding electrode system? those terminology, those questions are not interchangeable. Precision does matter in this case, especially with grounding and bonding. It's probably one of, again, the vastly misunderstood concepts, and it's why in our program, our grounding and bonding course is so popular, because we break these essentials down and understand that they're similar but different. Especially when we're trying to diagnose why current is flowing on paths that it's not supposed to. And the example we gave was using a bonded generator when we're not switching the neutral on a dwelling. That can create that kind of condition, and it's an unsafe condition. The next one that we get from people, I just go on and get it out there, is the ground rod myth. While we're on generators, we might as well clear this up, because it's another misconception. Somebody sees a generator and immediately the first things that come out of their mouth, and cities are notorious for this, municipalities will say, you need to drive a ground rod. And they think that the ground rod is what makes a branch circuit ground fault clear. Okay? They think that that's what causes it to do that. That usually is a misunderstanding of fault current paths. Okay, the earth is generally not the intentional low impedance equipment fault current path we're depending upon to operate a circuit breaker's overcurrent protection device. That's not what we're doing with that. Y'all know that. The impedance on the earth is way too high. That's why our bonding and equipment grounding conductors matter so freaking much. Driving electrode into the earth doesn't magically solve an incorrect neutral to ground bonding arrangement. And removing the required bond isn't correcting an installation by installing a ground rod. Okay? Again, follow the current back to the source. That's the question. It's not a question of, does somebody install enough stuff called ground so that you have multiple connections that's going to make it better? Again, that is not what it is. So let's talk about why is bonded generators may appear to work perfectly on a system. And so you're installing it on a system and it's not supposed to be. Let's kind of figure out this real quick. So here's what makes the duplicate bond problem particularly deceptive. So this is where you mistakenly take a neutral that's not switched on a dwelling and you install a bonded generator onto that system and everything seems to work, right? It just seems fine. So everything may appear to be completely normal. The generator starts, the lights come on, the refrigerators work, the well pump runs, televisions come on, nobody gets shocked, and somebody says, see, it's wired correctly. No. Operation is not proof of proper grounding and bonding. It could be a ticking time bomb. Parallel neutral current paths don't necessarily stop equipment from functioning. That's the great thing about electricity is people do things wrong, it still tries to work, it still tries to function. The load can operate perfectly while some normal grounded conductor current is traveling through paths that were never intended to carry current under normal low current conditions. And then that's the problem. That's what makes grounding and bonding errors so deceptive because it still works. The system can work and it's still wrong. That's what creates a hazard, and that's where you end up having current traveling on parts that they're not supposed to, and it's just waiting for you to come along and touch it and come in contact with it. So here's a little exercise. Just kind of put you in a perspective. Every electrician should sit down and draw this. If you're ever confused about generator installations, stop arguing about terminologies and getting confused in it. Let's do this. Just take a piece of paper. Draw a generator winding. And you have line 1 and draw line 2. And draw a neutral. And draw the generator's frame. Draw the equipment grounding conductor. Draw the dwelling panel. Draw the service bonding connection. Then ask yourself as you're starting to draw this up, is the neutral switched? That's your first question. If it's an interlock system, no, it's not switched. So if that's the case, trace to neutral all the way from the generator back to the dwelling unit, then locate every connection between the neutral and the equipment ground. If you got one at the service and another at the generator, draw the parallel paths. It becomes painfully obvious that if the neutral is switched, then you don't have the same condition if the neutral is not switched, because current's going to be circulating on all those paths back and forth to the generator on the equipment. But if the neutral is switched, draw what happens when the transfer switch moves the generator to the generator position, where that neutral is disconnected. Now, ask whether the generator system is electrically separated from the other systems, including the grounded conductors. Obviously, if you're switching the neutral and you're switching all the ungrounded, you are. So you're creating two separate systems. You won't have parallel paths. So this is why I tell electricians constantly, draw the circuit. The code becomes a lot easier when you understand the electricity underneath it and how it flows. Now, UL 943 isn't just an old 5 milliamp standard. That's another thing worth understanding when it comes to UL 943. It isn't frozen in time. People talk about GFCIs like nothing has changed since the 70s, but modern electrical systems are full of electronics. Variable speed motors, inverters, power conversion equipment, switching power supplies, vastly changing electronic equipment, smart technology. All those technologies can produce something called high-frequency leakage components that older discussions of GFCIs rarely address. In August of 2025, UL Standards and Engagement issued a revision to UL 943, adding supplement SB for an optional high-frequency or HF rating. UL says that the HF rating addresses compatibility with modern loads producing high-frequency leakage current, including loads involving variable speed drives and inverters. UL also notes that the 2026 NEC recognizes this new Class A HF marked GFCI application. So, when we say UL 943 GFCI, we're talking about safety standards that continue to evolve with the modern electrical components. This is why electricians need to understand both the fundamentals of how the circuit operates, the principles, and you also need to understand the product standard behind the device. So in a rapid succession here, let's kill the myths one by one really quickly and wrap this thing up so you can have some real clean takeaways. Number one, GFCI needs an equipment grounded conductor to work. That's false. Its basic personnel protection sensing function is based upon differential current through the monitored circuit conductors, not the equipment grounded conductor. Totally different thing. Myth number two, a GFCI monitors the green or bare wire. False. As description of basic Class A operation, it's comparing monitored circuit conductors. The EGC, or equipment grounded conductor, may provide a path that creates an imbalance, but that is different from saying that the GFCI is simply measuring current on the equipment grounded conductor, because it's not. It's actually sensing the imbalance between the neutral and the hot in those monitored circuit conductors. If current travels on the EGC, all that's doing is going outside of that toroidal coil, and that is giving it another path back that will cause the GFCI to function. But it could be other paths back to the source outside of that toroidal coil as well. So it doesn't mean that the GFCI is monitoring any equipment grounded conductor, because it is not. In fact, we've established that it doesn't even need it to function its intended role. Myth number three, GFCI makes an ungrounded receptacle grounded. False. A GFCI protected and an equipment grounded conductor are two different things. GFCI protection, again, looking for those imbalances, whereas an equipment grounded conductor is providing an effective low impedance ground fault current path back to help facilitate the operation of an overcurrent protected device. Vastly different concepts. One does not replace the other. Okay? Myth number four, a GFCI will always protect me if I get shocked. False. If current leaves through one monitor conductor, travels through your body, and returns completely through another monitored conductor, there may be no differential current. Again, touching the hot and the neutral, and both of them happen to go through that coil, there's no differential current. So in all cases, it will not protect you in all situations. UL specifically warns that GFCI protection is not provided when contact is made with more than one of the circuit conductors that is running through the protective system. Very important to understand that. Number 5. If my plug-in tester doesn't trip the GFCI, then GFCI is bad. Not necessarily. Many external testers need an equipment grounding conductor path to manufacture their test imbalance. And OSHA specifically says a negative external tester result alone isn't conclusive. Myth number 6, a floating generator can never shock you. False. The first conductor to ground contact on a truly isolated floating source may not establish a strong enough return path for real-world capacitance, leakage. Okay? But a real-world capacitance, leakage, connected equipment, and additional faults can change the system. So the initial connection, it may put enough current through you that is not enough to cause the device to function. That does not mean in all cases that you can't get shocked. But again, in real world, various capacitance, leakage, connected equipment, or additional faults can change the system and provide a path back, an alternate path back where it doesn't go through the coil and that it could protect you. But at what cost? Because it may be the initial shock that didn't cause the device to function properly because it was floating and used in an improper application. Vastly important to understand the differences. Myth number 7. A GFCI doesn't work on a floating generator because the GFCI is defective. Not necessarily. If there isn't enough differential current because there isn't an effective return path, as we just talked about, the device may simply have nothing substantial to detect. That doesn't mean the GFCI is defective or bad. It's just not enough imbalance for it to go off. And remember, UL identifies a Class A UL 943 GFCIs as intended for a grounded neutral system, not to be used on systems that don't have a grounded neutral. Very important to understand the application of a Class A UL 943 device. Myth number 8. A bonded neutral generator is always safer. False. If you're connecting that generator to a dwelling, right, through an unswitched neutral arrangement, another neutral frame bond can be established and creates parallel neutrals and equipment grounding paths, and that could potentially energize metal parts that were not designed to carry current under normal operation, only under a fault condition. It creates a touch hazard. Myth number 9. A floating neutral generator is always safer. Okay, so we went from a bonded neutral one and we explained why, if you're using it on a dwelling, it's not safer. Then what about this? Again, a floating neutral generator is always safer. That is also false. If the transfer equipment switches to neutral and it truly creates a separately derived system, the proper system bonding arrangement is different. And you need to have that connection. So you have to evaluate each system's configuration separately. If it's switching the neutral, then we need that bond. If it's not switching the neutral, we do not want that case to bond to be done on that generator. kind of understand these concepts. And if you don't get it, rewind this back and listen to that portion where I talked about it. Myth number 10, if the generator powers the house, the installation must be wired correctly. Okay, let me read this again. If the generator powers the house, the installation must be wired correctly. So just somebody sees the generator hooked up to the house and they assume that everybody did the right thing. And just because they plug a generator in and all of a sudden everything gets powered on, refrigerator works, TVs work, everything, you assume, hey, everything's okay. Generator works. That it must be done correctly because everything's working. As you heard before, that is absolutely false. An improperly bonded system can operate loads perfectly while still allowing normal current on an unintended conductive paths creates a hazard. So just because it works doesn't make it right. So 3 questions that solve most generator arguments. When somebody asks you, should this generator be bonded or floating? Before you answer these questions, question number 1 is this generator operating standalone or is it connected to a premise wiring system? Huge difference. That's the first question that you as an electrician should always ask. Where is your intended use of this generator? Number 2, does the transfer arrangement switch the neutral? That's one of the biggest questions in the entire analysis. And if you haven't figured out by now, that's going to dictate your generator connected to your dwelling on whether or not you switch the neutral or not, on whether or not it's a bonded or unbonded generator. Got to ask that question. Question number 3, where is the neutral to ground system bonding connection for this operating configuration? Is it at the generator or is it at the panel, service panel? If it's at the generator, then you need to transfer switch. It transfers the neutral. If it's not at the generator, but the connection is neutral, the neutral to ground is made in the panel, then you want to make sure that the generator, and you're not switching the neutral, that the generator does not have that bond connection between the neutral and the ground. Make sense? Once you answer these, you've analyzed the circuit. You know where to go together. So let's go all the way back to the beginning. Why can't a GFCI function without an equipment grounding conductor? Because the GFCI isn't dependent upon the presence of an equipment grounding conductor for its basic differential current sensing principle. It compares current. That's it. Why might a first conductor to earth contact on a truly floating generator not cause the same GFCI response? Because there may not be an effective current path back to the source. And so the GFCI device cannot detect the differential of current flow. That's why. Why does connecting that floating generator to a dwelling through an unswitched neutral change the picture? Well, because now the generator's neutral is connected to the dwelling's grounded conductor system and its service bonding point. That creates what? A situation where you get parallel applications. So we have to understand that if we're going to switch the neutral, then we want the generator to be bonded. If we're not switching the neutral in the panel, then we want the generator to be unbonded or floating. Make sense? Okay. You might ask yourself, why don't we just leave another neutral to frame bond at that generator? Why does it matter? Because with the unswitched neutral, again, we create a second neutral to ground connection and those parallel paths for normal neutral current traveling on conductors that never intended to, making contact with parts that are bonded to the equipment ground that now have current flowing on it. That's a problem. That's a hazard. Doesn't mean it won't run. It just means you're creating a ticking time bomb and a potential lawsuit if you don't know what you're doing and you're an electrician. Well, what if my transfer equipment actually does switch to neutral, Paul? Now we change the system configuration again. And now you may have a separately derived system. requiring an appropriate bonding arrangement. That means that you, again, want to that point make sure that if you are switching the neutral, and I keep doing this repetitively so this hammers in your head. If you're now switching the neutral and you have a separately derived system, then the generator is treated as such. And that's when it needs the bonding jumper in there between the case and neutral, because we're truly switching the neutral in the panel because of a transfer switch. Hopefully that makes sense to everybody. What's common through all this is the current path. There's no slogans, there's no folklore. There's not, I've always done it this way and it's worked. We understand that current has to leave and it has to return, and what conductive paths exist between the source and the load that allows for that. So if you remember one thing from this episode, and we've been an hour and 30 minutes approximately, if you remember only one thing from this podcast, remember this. A GFCI isn't really asking, is current going to ground? It's asking, did all the current that left through my monitored conductors return through my monitored conductors? If yes, the GFCI sees an imbalance. If not, it sees differential current. Once you understand that, suddenly all of these issues start to make sense. Why a GFI operates without an equipment grounding conductor. Why an external GFI tester may not function. Why grabbing a hot and neutral simultaneously is still incredibly dangerous. Why a floating source behaves differently. Why the first fault and second fault on an isolated system are different events. Why unswitched generator neutrals matter. Why a duplicate neutral to ground bond can create parallel current paths, and we just talked about why that's inherently dangerous. And why a switched neutral transfer arrangement completely changes the grounding and bonding analysis and means that it's vital to whether or not you choose a bonded or unbonded generator. Vitally important. This is electrical theory meeting electrical safety. And this is exactly why we shouldn't teach electrician rules without teaching them why these rules exist. Because if you all know is that bond this, ground that, put GFCI here, you start memorizing instructions. But when you start to truly understand the source, the circuit, the current path, the bonding, the differential current, when you start really understanding that, you can analyze it. This is what makes electricians true electricians. Not just repetitive soldiers that simply do this from A to B. And this is why we teach people, because we really want you to understand it. So the next time somebody tells you, quote, a GFCI needs a ground wire to work, don't just tell them they're wrong. Show them the toroidal transformer. Show them the current going out. Show them the current coming back. Show them the floating generator and how it works. Do that little diagram. Then do the same one and connect the generator to an unswitched neutral dwelling unit. Then show them what happens if you add a second neutral to ground bond with the generator. Because look, the best way to eliminate misconception isn't to replace one slogan with another. It's to literally teach them how the circuits function. And that's why we should be teaching GFCIs, grounding and bonding, and generator system. Understand the current path, and the rest starts to make sense. Hopefully you got something out of that, folks. It was a long one today. Hopefully you made it through it. If you have any questions, you can always put it down in the comments. Feel free to yell out to me and let me know if you want me to clarify anything. I try to give you everything I can in an episode, but those are the fundamental concepts of how the device functions. If you disagree with that, you're going to have to bring the receipts, because that is essentially what it says in UL 943. That's what it essentially says in OSHA, and this is how they function. It's common sense, but sometimes it gets mixed up with folklore. Till next time, folks, stay safe. God bless.
Thanks for tuning into another electrifying episode of the Master the NEC podcast. We hope you're feeling more powered up and ready to tackle the electrical world with the knowledge and confidence you need to succeed. Remember, in the electrical trade, knowledge is power, and we're here to make sure you stay plugged into the latest insights, tips, and code updates. If you enjoyed today's episode, don't forget to subscribe, leave us a review, and share the podcast with your fellow electricians and industry pros. Until next time, keep your tools sharp, your circuits clear, and your mind focused, because here at the Master the NEC podcast, we're all about sparking your success. Stay safe, stay smart, and keep mastering the trade. From all of us here at Electrical Code Academy, thank you for all your support, and we will see you on the next amazing Master the NEC podcast episode.